An extension of the Bronsted-Lowry definition of acids and bases is the concept of the conjugate acid-base pair. It can also be defined as an acid and its conjugate base, or a base and its conjugate acid. To understand this, we have to look into what we have known about the Bronsted-Lowry theory of acids and bases. We do know that acids, based on this theory, is known as the proton H+ donors, whereas the bases, we know that the bases based on the Bronsted-Lowry theory, they are the proton acceptors. Therefore, when a Bronsted-Lowry base accepts a proton from the acids, the species form is called a conjugate acid. Conversely, when a Bronsted-Lowry acid donates a proton we're going to form the conjugate base. Let's have a look at one example over here. We know that HCl is your acid, and this one will be your Bronsted-Lowry acid. It will be able to donate this H proton to your base, water, and this water molecule will act as the Bronsted-Lowry base. It will accept the proton from there. So when this one is your acid, this is your over this side, you can see that this is in the beginning was part of the HCl. This guy over here will be your conjugate base. So this is the pair of acids and the conjugate base. So what happens to the water? In the beginning, the water molecule over here behaves as a base because it will be accepting the proton H+ from HCl. As you can see, this is what happens to the H2O. It will be accepting the proton from the HCl, so that is a Bronsted-Lowry base. So after the reaction moves forward from base, it will be your conjugate acids. Therefore, this is the pair Let's have a look at another example. Right here, we have a very typical exam questions when they want you to identify the conjugate acid-base pair in the following reaction. We have to identify which one is going to be the conjugate base, which one is going to be the conjugate acid, and so on. So let's have a look first. Right here, we have NH4 plus aqueous, and we have OH minus aqueous. If you look on the other side, NH3, this species looks similar to NH4 plus. And then H2O looks very similar to OH minus. So what can we see the difference here? When NH4 plus aqueous as the reactant react with your OH minus, what happened here? This NH4 plus will donate the H plus to your OH minus to become NH3. In the beginning, you have 4H, and then after the reaction moves forward, the NH4 plus will lose one of the H to become NH3. Therefore, what can we conclude? This is going to be your acid, and the pair right here would be your conjugate base. Okay? So that's how you're going to answer that in exams. You have to circle that. You have to circle that one too. You have to identify this one is the acid. And on the other side of the reaction, you're going to have its conjugate base. Remember, if you have the acids right here, the pair would be your conjugate base. If you put acids and here conjugate acids, that is incorrect. Now we have identified the acids and the conjugate base. Therefore, this species right there, OH minus, would surely be your base, and this one will be the conjugate acid. So that's how you're going to label it. By doing this whole thing over here, you would be able to get 1 mark. Okay, so usually they're going to give you 1 mark for labeling, like this. What about this example right here? So we're going to employ the same kind of strategy. First, we have to look at your reactants. We have CH3 NH3 plus aqueous and CN minus aqueous. When you move to the other side of the reaction, CH3 NH2 aqueous looks very similar to CH3 NH3 plus, but this species over here has fewer number of H. Therefore, I can conclude that this one is your acid because it will donate one of the H to your CN minus. And what happens to this after the donation? It will turn into CH3 and H2. So that is quite clear. This would be your conjugate base. Thus, Cn minus would be your base, and this will be your conjugate acid. After labeling in this form, you would be able to get 1 mark for identifying the conjugate's acid-base pair correctly.